Oh, yeah.
¿Mandado el link?
No. Porque no encuentro el email de Carliños para contestar.
Era esta semana.
Pero voy a hacer eso.
Es del día 25.
El día 25, dice.
Presentaciones becarios de verano. Los que se quieran conectar. Creo. Okay, all right. All right, so welcome, thanks for coming. Today is the usual seminar of the 3 summer students who've been enjoying the summer in Teruel. This summer was particularly fresh, and the nice thing of the summer studentship is that it basically starts with vaquillas, so you couldn't start better. And the 3 students are Antonella, Laura, and Alejandro, and we're following that order because they decided to do so. All right, so Antonella will start.
Hi everyone, I'm Antonella Schenone Zanuzzi. I'm going to present my project I'm working on during my summer studentship in astrophysics at CEFCA. The title is Automatic Classification of Variable Star in J+ Year 3, and my supervisor is Alejandro. So, variable stars are very important in astrophysics, and variability can have many different causes. We can see this in the Gaia variability tree. And the tree shows 2 main blocks, extrinsic and intrinsic variability. And extrinsic means effects outside the star, like eclipses or rotation, and intrinsic means change inside the star, like pulsation or erection, for example. The main objectives in the project are to automate variable star classification in J+ with machine learning, deliver a validated and robust catalog, and guarantee astrophysical consistency. I used 2 complementary astronomical surveys. First, Gaia Data Release 3 from the European Space Agency. It provides precise astrometry, multiband photometry, and variability classification. It is the largest homogeneous catalog of variable stars to date, and is currently the main reference for variability studies. Second, I use the J+ Data Release 3 from the Javalambre Observatory. It provides 12-band photometry, sends to its unique filter set and high data quality. It's ideal for multiband analysis and provides robust stellar parameters. Together, they give very rich information for variable star classification. At the beginning, I thought it would be simple, just data downward, cross-match between Gaia and J+, apply machine learning model, and get candidate. But in reality, it's very difficult todo esto, and the process was more complex. First, I needed to clean the data. I applied astrophysical filters. After that, cross-match between Gaia and J+. And for classification, I tested different machine learning models. For example, balanced random forest, KNN, and neural networks. I also used the data augmentation to balance the data set. And finally, I obtained candidates and validate them with astrophysical checks. So now, for J+, I selected source with high quality photometry and contaminated measurements. And for Gaia, I use only stars in the northern sky and avoid the galactic plane. I use these criteria in the queries. Then I apply the astrophysical preprocessing I consider only positive parallax with a relative parallax error lower than 20%, and with this I calculate the absolute magnitude with parallax data from Gaia. The maps show the area of the sky covered in J plus DR3. After applying all the filters, the numbers were smaller. The bar plot illustrates how the initial million of sources in each server progressively reduce after applying the quality criteria. In these steps, I combine the Gaia and J plus datasets after filtering and preprocessing. I use a positional cross-match in a radius less than or equal to 1 arcsecond, and the cross-match produces a final catalog of 44,000 objects. These are the sources used for the classification. The final filtering method keeps only classes with more than or equal to 0.1% of the total sample, and only the top 35% of Gaia classification score for each class. The Gaia classification score is describes a quantity between 0 and 1 and is related to the normalized rank of the classifier's confidence. Before filtering, we had many classes. After filtering, only 8 classes remain. Solar Light, Delta Scuti, Gamma Doradus, SX, Phoenix are the same class. R is Carnum Venaticorium, Eclipsing Binaries, R Relira, Cataclysm Variable Star, so Dwarf B stars, and White Dwarfs. The HR diagram shows these classes, and we can see that the sources are in the spectral regions, which confirms the quality of the catalog. The final catalog contains only rows well-populated and high-confidence classes. Flags were normalized to the maximum value. This way, we can directly compare the spectral energy distribution shapes. And here we can see an example with the normalized flags for the 5 brimming stars in apparent magnitude of each class. Each class showed a different set curves, and this is very important because the diversity of set shape reflects the physical variety across the stellar classes. This also showed that the catalog is astrophysically consistent and are important for training and validating classification models. For the classification tasks, I used machine learning model. I tested 4 main algorithms with 2 extra variants, in total 6 models. First, I tested the balanced random forest with use decision trees. Then the balanced random forest with principal component analysis, which help reduce the dimensionality. Also, I used the KNN, which classified based on the neighbor. And for neural network, I tested 3 models. The multi-layer perceptron, a simple neural network. The MLP with Simba cross-match, using only object where Gaia and Simba classification agree, fewer object, but more reliable. And finally, I used the MLP with multi-level binarized, which allow multiple levels. In simple words, the process is use 70% of the data, apply the model, and 30% to test its performance. I apply the model to the test set and obtain the performance metrics, where F1 is a balancing precision and recall parameters, and accuracy is the total correct prediction. The macro F1 is average over I classes in equal importance, and the weighted F1 is average by class size. Looking at the table, we see that the MLP gives the best results. And the MLP with multi-level binarized does not have accuracy because accuracy is not defined for multi-level classification. In the end, all models reach a similar performance limit. To overcome this limitation, apply data augmentation to balance the classes and improve machine learning. Some classes had many stars, but others had very few. To solve this, I used data augmentation. I increased each class to 90% the size of the largest. The largest one is solar light. And I generated new objects between Gaussian noise in 1 sigma for every filter in J+. This simulated realistic star without changing the physics in the sets. After augmentation, all classes had around 8,000 stars, and this gave a balanced data set, and which is very important for machine learning. I normalized all fluxes to ensure consistency across the dataset. Before augmentation, the best model had accuracy around 0.85, 0.82, 0.86. After augmentation, the results improved a lot. So, without augmentation, the models are stronger, are more reliable, and because the classes are balanced. The balanced random forest with principal component analysis was discarded because reducing the dimensionality clearly, reducing the dimensions clearly, they lost important information. The diagram below shows the next steps. We apply the training model to my J+DR3 data, obtain the candidates, and finally check the results in a shared diagram for astrophysical validation. This method is important because it's independent of the machine learning models. So, some models place stars in regions that are not physically correct. This is an example of MLP with Simbad crossmatch. The conclusion is a smaller and more accurate dataset sometimes those means is better. MLP with multi-level analysis leads to many objects unclassified or ambiguous. Many star overlaps in different classes, and many others are left without classification. The MLP model without Simbad produced the most astrophysically consistent results. I used this model for the final classification. On the left, we see all the predicted classes with probabilities larger than 0.9. For example, in this case, solar lights means are on the main sequence. And on the right, I zoom on the rare classes. For example, in this case, white dwarf in gray are in the lower left, and subdwarf in yellow are above them. So, in the conclusion is that the MLP prediction are astrophysically consistency with the stellar evolution, and classes are generally located in the correct HR diagram regions. I validated some automatic classification by cross-matching with external catalogs, external variable star catalogs, and the HR diagrams show the position of two RR Lyra candidates. Those objects have been identified by the model, and the model have never seen them before. This is very important part. And we see their light curves and confirm the characteristic shape and the period. To summarize, I developed automatic pipeline for value state classification using Gaia and J+. I built a balanced dataset using data augmentation for further training of the model. And the catalog is astrophysically motivated because filtering ensures the reliable stars. The neural network multi-level perceptron model gave the best results, and with the highest accuracy and more consistency position in the HR diagrams. The results were validated with HR diagrams and with external catalogs. For the future, with Alejandro, we want to test the Gaussian mixture model and apply the pipeline to new J+DR4. Thank you very much.
Questions, comments? I cannot ask questions. It would sound like
No,
arranged.
Alejandro.
All right, I go. Your last color diagram magnitude.
Yes.
One of the last ones. This one. It looks different than the one that you made the cross match with Gaia.
Yes, the before I share diagram is the data set for training the model. This is after I apply the model of my J plus data.
All right, and if I recall correctly, you mentioned that you had like 40,000 cross match with J plus and Gaia.
Yes.
I mean, we're talking about stars that have been classified as variable. No,
Yes.
Okay, right.
In these classes.
All right.
And after apply the filtering, I obtained only 8 classes.
And you're training your neural networks using the flux.
Yes. The normalized.
Why not to try the magnitude?
Why? Because in the magnitude case, I need the distance for the absolute magnitude.
I'm talking about the relative magnitude.
Yeah.
The apparent magnitude.
I don't know why.
Normally, the flux gives better results. The magnitude squashes the result.
But then you validate it with the magnitude.
And you don't validate.
No, this is, I don't know. Try both.
I actually tried previously, and yes, flux works. Flux is normally much better. And we don't validate. It's a visual confirmation, but the whole network works in normalized fluxes.
Yeah, well, I'm just asking because the magnitude is something you measure directly. The flux, you need a calibration. It is a step. Yeah. I mean, if you are not able to flux calibrate correctly, probably you are not going to. I mean, the magnitude is something you measure directly from the instrument. So if there is a variability, you should be able there directly. But with the flux, you may have to step between that. I'm just guessing. It's the first thing I'm thinking about.
I beg to disagree on you don't measure the flux as you measure the magnitude. You actually measure the flux and then you infer the magnitude. What you measure on a CCD is the flux.
You're measuring an instrumental magnitude.
Yeah.
Yeah, and then
No, you measure flux in ADUs.
But in any case, in J plus it is calibrated. No?
Yes.
In J plus, both magnitudes and fluxes are calibrated.
So yes.
Maybe.
Yeah, I do have a question. I will come in. I can support your idea to use fluxes because for variable stars in general, not just IR units, fluxes are used rather than magnitudes. For the
I do one more question if we have time and the same plot with the color magnitude diagram. Yeah. The final one. So yeah, here or the previous one, whichever is fine. You have a lot of objects overlapping in the same region, right there.
Yes, I am.
But then you're saying those are of different classes.
Yes.
And like, so they have some other features that you use to describe these objects. These are the predicate classes, not the training data set.
Sorry, can you repeat?
No, I'm just like confused, like you have different objects in the same,
This.
yes, for example there. But then like they are classified
Yeah,
as
the
different
model of
objects.
course is not perfectly.
Okay,
But it's a better model.
I see.
Yeah. For example, the eclipsing binaries here. But it's more clearly than other models. Too much error in the white dwarf regions. This is better than others.
Hector, and then we move on.
Okay. Very nice presentation. By the way. Can you show the different SEDs,
Yes.
different types? Extra common. I agree with taking the Gaia classification of variables, which is like low number of types. But for the solar-like in particular, where you have a lot of sources, it's difficult to say anything about them. I think here, actually, by the SED, you can distinguish between two large types, which are the Canis venaticorum type,
Yes.
which are I mean, and the BY draconis,
Yes.
which have different spectral type, and actually you can see like there is a mixture there in the spectral type. So this is a case where the spectral information is giving some advantage with respect to the time domain, because the records are similar. Just to
In this case, the Gaia classification for the solar light is not clearly.
it's like
Yeah, everything.
everything that is left.
Main
no,
sequence from
Yeah.
solar light.
Yes, a very short comment. So, congratulations. I think this is a great piece of work, particularly taking into account that this is a 3-month summer. 2 months. So even I will insist on my comments. So congratulations to you and Alejandro. I think it's very, very interesting. It's a good starting point for a future research project that, if you have the interest and the opportunity, I think there is a lot of potential there. I only have one minor comment with respect. If you can show the last 2 CMDs you showed before, the 2 color magnitude diagrams that have been discussed several times. So do you have, probably you mentioned that, if that's the case, I know that, but do you have an estimation on how clean this candidate list and how complete this candidate list is? So how clean is, what is your level of confidence on the selection of the candidates and the type of candidates, and how complete do you think you are finding all the candidates or a fraction of them? I mean,
A fraction of them I validated with a Simbat cross match. When my model I'll confuse the classic, usually is normal confusion. I don't know. For example, RR Lira usually confused with hot branch stars in Simbat catalog.
But you don't have an estimation on that? Or
No.
You don't have
No.
it?
Maybe
That-
for
that
the
would be
future,
interesting
yes.
to have
with
in the future.
with an extra month.
I
Yes.
guess that could be for the first one. Okay.
But the models, I have the usually correct prediction in different classes. My model is this, and the diagonal is the correct prediction as well.
Okay. Very interesting.
All right. In the interest of time, we move on to the next speaker. So let's thank. Okay. Opa. Vega, unmute yourself and comment and say it while we change speaker.
Yeah, no, I was saying that related to the last question, the different metrics such as precision and recall can give you an idea of the completeness and the purity of your classifications, and also you can improve a little bit the uncertainty of your classifications using different models or different trainings for the same model as Antonella was presenting. So yeah, there is a way to try to characterize the completeness and the purity of the classifiers. But apart from that, very nice piece of work. Congratulations, Antonella and Alejandro.
Thank you. Sí. Necesito cerrar esto.
Aquí. Ahí arriba, llegas.
Oh, la.
Epa. Ahí.
Cuando tenga que pasar. Bueno, hay personas.
All right, so the second presenter is Laura, and so I'll tell you when you have 5 minutes left.
So, hi, good morning, everyone. My name is Laura, and today I'll present you my summer research here at CEFCA, which consists on a systematic Blackbody white dwarf search in the J+DRP catalog. So, yeah, we're gonna begin with an introduction here about the classification system of the white dwarfs, because I don't know if everyone of you is familiarized with it. So, yeah, the most important ones are DA, DB, and DZ, which consists on if they have hydrogen, helium, or no absorption lines. So this is an example, so you can see visually the absorption lines here, DA, DB, and the non-absorption lines here. But yeah, this is you can have another parameters taken into account, but these are the main white dwarf classes. Yeah. We're gonna study, as I said, the Blackbody white dwarfs, and what's that? Once you may already begin to think of Blackbody white dwarf, this is a white dwarf that has a Blackbody-like spectrum. So here it's the magnitude versus the wavelength graph from the paper from Suzuki and Akita in 2018. So it's very clear that the points here follow a Blackbody spectrum. And there's just been 17 Blackbody stars discovered in the SDSS, in the Sloan catalog. So in this study, it's just been serendipity. In this study, we're doing the first systematic search for this kind of objects. Yeah, it's just applies the residuals. And if you have questions, you can ask me. Yeah, I don't want to keep on talking. So I guess you're all very tired from seeing this kind of figures, but this is a little promotion time for data. So in this study, we're going to use, as I said, the G+DFTV catalog for white dwarfs. These are the 12 optical filters, and these are the sky distribution from the white dwarf catalog. So these were the data we'll be using in our study. Okay, so we begin by plotting every white dwarf we have in the catalog. There are more or less 15,000 white dwarfs, but we do a selection here of the color diagrams for the bright stars, meaning magnitude 16.5. So here is the hydrogen and helium sequence pretty clearly that if we plot every star, we don't see that. So yeah, and here this kind of plots is it's an example. Of course, you can do a lot of combinations of the same plots, but here you have J -1, -1 I, and here is different filter versus minus R. So it's kind of different but similar in every plot here. And this the color band here represents the probability of H, PDA. These are DAs and these are DBs or DCs. Yeah, as I said before, there were several candidates discovered by Suzuki and Fukutita, and we did a cross match with our catalog here, so we can see how many we have now in J+. And we have 5 of them, so we plot them here too, and it's what we expect because they appear on this band, this social lines. So we say they are black bodies, so they don't have to have social lines. So it's what we expect here. Okay, so now we're gonna do synthetic black body photometry. And why do we do this? Because we want to do a systematic search and we want to do an MCMC, Markov chain Monte Carlo analysis. So we have to have a model to compare it with. And this model is going to be, of course, a black body model. So these are the same kind of plots that I did before, but we did a synthetic photometry with different temperatures. So they are plotted here in dots. This is the model we're going to be using and comparing to the data we have. So we start with these 5 candidates that I said earlier, and we got here the magnitude and the wavelength as before, and the residuals. So this was done by, as I said, our UCM statistical study and MCMC, and we left 3 parameters that are the temperature and the normalization. So as you can see here, the real stars are the synthetic PV photometry, and the dots, the pink dots, are the observed photometry. So yeah, it's what we expected because these are supposed to be black body stars. So yeah, it appears that it's just compatible with that. The errors are between around 0 and around 1 sigma. So that's what we expected, and the results are these ones. So the correlation between normalization temperatures, of course, again, we expect, and these are Gaussian-like stuff, so everything's like correct, like validating our methodology. And these were the results that maybe like these, they don't tell you much, but we can compare them to the literature, we can compare them with what they obtain, with the temperatures they obtain. We have this plot. So the dashed line is the identity. Well, in this axis, we have the previous study temperature, and this is our temperature obtained here. So in the dashed line, as I said, it's the 1, the identity. These are the 5 black body stars. And as you may have already noticed, there's a slightly offset here, but it's very small. It's a relative power of 1.5%. So it's a very minor systematic offset, and it's likely due to calibration differences. So we're happy about these results. So now we can now that we have assured that our methodology is correct, we can do this systematic search that we were looking for. So here, Vega doesn't allow us to see that, but the white dwarfs in J plus G3 are 100, and as I said before, 15,000 more or less white dwarfs. But if we do a pre-selection of our candidates with the magnitude, selecting the ones that are right at that 18, there are like 1,300 more or less stars. And then we do a final selection of temperature there. We select the ones that are below 25,000 Kelvin. We end up with a set of 640 white dwarfs. So we run again our analysis, our MCMC, and we obtain chi-square like this. This is a distribution of chi-squares obtained. This dashed line here represents the 23.2 chi-square, and it's because from here to the left, it's like breaks this whole black body, and from here to the right, it isn't. It's considered like outliers. Yeah, that's because we have 10 degrees of freedom in our analysis. We have 12 points from the pixels, and we have 2 free parameters, so it's 10 degrees. And yeah, this is the one that is used for our kids. Yeah, we can do zooming to see the ones that are to the left of 23.2, and we see that they're very few, compared to the data that we use. So now we can plot this. I'm going to start right here. Here we have the temperature versus the chi-square, so we can get insights of what they look like the properties. So this one, this little star here, is the candidate for which is very relevant because it's the one that it's in the previous study. It's the only one that I have here that is from the previous study. And the first image that I showed you about a Blackbody star was this one. So it's everything, it's perfectly. So yeah, it has a very low chi-square, as you see, at 6.81. The temperature is like 10,000 Kelvin. And this is the rest of dots, the gray dots, it's every white dot in our analysis. So as you can see, when we have high temperatures, the chi-square is very, very high. And when we go to lower temperatures, the chi-square tends to go lower too, but it's not as low as it is to take into account that it's a Blackbody white dwarf. Because it's because when the stars are colder, they have the spectrum, the absorption lines may disappear, so they appear to be at DC, but they are really not. It's just because of the temperature. They're so severe. So yeah, that's like again what we expected more or less to see. Here we have a selection between the ones that we consider that are not Blackbody candidates and the ones that are Blackbody candidates. Using our chi-square obtained and the chi-square obtained from the data of the catalog, because they have, of course, a chi-square in the catalog obtained with physical models that are not a Blackbody model. So the ones that are, it's normal, that our chi-squares are very, very higher compared to the ones that are on the catalog, because they're like the physical model they need to have. But there are a couple ones that are below or near the identity here, and these ones are selected, of course, from 23.2 to the left. Other ones, of course, are, as I said, near this spec. So we ended up with 21 Blackbody candidates here from, again, the 600 books. These are examples, so you may see how, for example, these are different temperatures. You can see the peak of the Blackbody moving. Because we start here in 11,000, and then we end up with 6,000. So it's kind of different, but they are all Blackbody candidates because, as you can see, they're very compatible between the synthetic photometry, Blackbody photometry, and the actual photometry. So at last, I want to remember that this is the first systematic search for Blackbody white dwarfs in J-Plus. It's not done, so that's very cool. And we obtain the results that we obtained corroborated ones that are from previous studies, so that's pretty good too. And we ended up with 21 Blackbody candidates that are more or less at 3% of the data that we studied. The future work here is, of course, to do this study for every star of the catalog, not just on a pre-selection that we did. And we should also do cross-matching spectra, and also I would really like to do separately detailed analysis from DAs and DTCs, but I need another month. So it's just future work for now. But yeah, this is not. And before you ask me your questions, now that I have you all here, I want to say that it's been a pleasure working with you guys, and you've been such a great co-workers, the best ones I could have asked for. So yeah, now that's it. That's for another moment. But yeah, now I'm happy to answer your questions.
Questions? I understand that the 21 Blackbody candidates that you have found in this study were not identified previously as Blackbody candidates. So how significant is this contribution to the overall number of already known Blackbody candidates?
I don't know, it's just there's not so much papers about it, it's like a couple papers of Blackbody withdrawal. So I don't know, maybe for the people studying these kind of things is so relevant, maybe for the astrophysical thing is not so relevant, but I think they're so relevant because you can. I forgot to say that, but you can of course use it for calibration because they don't have social life, so it's very important, I think, for those kind of works. So I don't know, maybe it is kind of important.
I'm sure it is. Are you expecting to confirm, I mean, to do a follow-up on those candidates?
I'd love
using-
to. That doesn't-
It partially depends on you.
No.
Of course, if you keep working on that direction.
Yeah.
So thank you very much. And again, I think that the level is very high in this year. So very, very nice work. Congratulations. I enjoyed a lot your presentation. Thank you.
More questions?
My question is, if only 3% of white dwarf of the white dwarfs are black-body white dwarf candidates, the remaining 97% of white dwarfs, why are they? Maybe they are black-body, but they are not candidates because they have maybe too many. The spectra doesn't align with the black-body spectrum, but for what reasons could a white dwarf not be in a black body state?
It's just the nature of the black body, of the white dwarf, because as you can see here, these spectra are quite different depending on the type of, the temperature, the spectral characteristics, all that. So full classification here, there was more, but I ended up quitting this. So yeah, if you have a continuum here, this could or could not be a black body, depending on the shape of the set. But of course, you have these kind of lines of calcium, for instance. If you have another metal, then they cannot be black body because the shape doesn't look like that.
Let me ask you the other way around. Why do these stars look like black bodies? Why are they black bodies? To look like black bodies, they must lack any kind of atmosphere. So they cannot have anything around which is cool so that it absorbs. So how are these objects which completely lost anything around them? What happened to these guys? What happened to these stars?
I think so. Just like, as I said, just that we don't have absorption lines, but I don't know exactly. I don't know if it's known in general exactly the origin or the. It's more like a study. Like we know this happens, so we study it, but I don't really. As I said, there are not so many papers about this. So just absorption.
Sorry.
The usual joke is that all stars are black bodies.
Yeah, of course. But no, sorry, not sorry.
We still have. Considering that the next speaker went to the bathroom, I guess.
Okay.
We still have time.
He was like, nope. So no questions.
That's a very embarrassing moment. Oh, okay, back. Sí. Antonella haciendo trabajo doble.
Siempre, como siempre. Ley de mi vida. Sabe que soy un desastre. ¿Cuál es tu carajo?
El que tiene coso blanco.
So, here, Pulsi Mall.
Oh,
Wow.
nice.
All right. So, as you know, every year we have 3 summer studentships. 2 are for the research area, and 1 is for the engineering. And so, Alejandro, I discovered like last week or 2 weeks ago that Florido was the first surname, it was not the second name. So Alejandro is the summer student from the engineering area. And
Ok.
te aviso cuando te hagas
Cuando siento-
mejor cuando.
Hi guys, I'm Alejandro. I'm physicist, astrophysicist, I'm mathematician. So this is far away from what I have been doing during my years, but I will be explaining the development and implementation of an AEA prototype to support the observatory, specific the kitchen. I will introduce you with the introduction, then to tell you what is a model context protocol and how to implement it in Docker. And finally, let's put our hands dirty to see what we can do. So, the introduction, no? We must know what is a LLM. For example, ChatGPT, something that acts like a human, you can interact with him and have conversation. Okay, you can have interaction with it. This is an LLM, but it doesn't take any actions. So we will provide him with tools, some tools that we define, for example, in Python, as I have done. For example, a tool could be a pencil to write, a hammer to hit people or something, or some sunglasses to see the next summer eclipse. So we have our tools, we have a model with you can talk. How do we do it to perform tasks? We define a model context protocol that is a standard way in which it doesn't matter so much which kind of model you choose, it will use always the same tools in a standardized way. So this will be an AA agent, something that not only talk, but also do something. Okay, where I will develop it in Flowwise. This is a way in which visually you have a node of start where you chat with it. You can see type your question. Okay. And the model will answer you. This is the place where I have been developing this. Later it will be more clear. But the part that is behind is called Docker. In it, the idea is to have different containers, and in each one you can install whatever you want. That is, for example, in Python, matplotlib, scipy, these all things could be here, not even in our own computer. It's something isolated of it. And this container, you can send it to other computers or to other servers. But for example, I've been developing this in another server. Okay, Docker, how does it work? You have something that you want to have in your server, or the model context protocol in a specific, or for example, the idea of a pen. You have a pen. With Docker, you take some kind of picture, and this picture you can run so much container as you want, and to have different visualizations of your image. For example, the idea of a pencil is to write down. So you can have a pencil to write in a paper in one container, or a pencil to write in a blackboard in another. But the idea is the same, is to write something. That's the idea of a container of an image. So my objective is to apply all this knowledge to the observatory kitchen, to create the model context protocol, that is what it costs me the most, and to deploy it using the containers, and finally, to see for yourself, as I have said. Then, the model context protocol, the main part of the work. what is it? What is it? I'm going to standardize, and I will use, for example, the idea of the Gmail. This model context protocol will provide you with some tools to send an email, to receive one, or to search for one. This is encoded in this model context protocol. And in our application, in Flowways that I showed you before, you can use these tools to access to the Gmail and to do different things. That's the main idea of the model context protocol. The implementation, well, un trabajo chino. You have to create a lot of Python files to connect between them. But the most important part is in this one, where I have defined the tools. But in total, all these files, it took me more than 3,000 lines. I don't know if it's much or less. For me, it was a lot. From physicists, more than 4,000. I have never, 400? Yes, have never done. So for me, it was a lot. Now, let's focus in this part, in the tools. In each file, we can define different tools to do different things. Guest operation, let's create one, let's delete one, let's obtain the full history, or if you want to update, hey, I wanted to read tomorrow, but at the end I'm going to observatory 2 days after. You have to create a tool to change that for every question you do to yourself. So that was the most difficult to build. So 42 functions to any question you can ask for yourself. Well, I only do it with myself, so it must be a lot more. So we have the model context protocol, all the tools, the functions. How do we implement it in Docker? Okay, we have Flowways, the application where I will interact with the LLM in one container, and the model context protocol that I have just shown you in another container. This model context protocol, it must be connected via a secure shell tunnel to the database. That is the picture one. And this is to provide a more secure platform. But these two containers, as I said, are isolated. We have to connect them in a Docker network, as it calls. This way, we can, from Flowways, to enter and to use the tools that we define there. So let's do the cool part. Okay, much talk, but show us something. So, que se me ha ido el VT. 1 second, guys, sorry. That was the sheet that I said before. Like, oh no, it went out. Okay. Now you can access to see this is the simplest things I have done just to show you. And in the note start, as I said, you have the chat input with which you talk with the LLM. Then a function that will give us the structure of the database, in which at the end of the day, I created just another container to do it. And the most cool part is the agent, in which we must define, we must do a specific model. For example, I took Grok, it's really fast and it can take the tools. And the OpenAI GPT-OS, that one model. Okay, and you can provide this model with some content, like for example, don't use more than so many times a function, or I don't know, respond in the language you are told, by default speaking English, or as I did in a video, Mario Bros. You can put, hey, act like Mario Bros, and it will answer you in this way. Okay, this is the idea. And here we have the container with the tools. And in this part, we can access them. These are all of them that I did and that our model can use. And the main idea, how can the LLM understand which tool use? For that, sorry, it is in Spanish. For example, this tool obtains just the ID and the username of the admins. So behind there is a SQL query, but the LLM just reads this. And if I ask to the LLM, hey, I want the names of the username from the admins, it will use this tool, just this one, so it can reason which one is the important. And in here, for example, I ask, can you provide me daily rate occupancy statistics, blah, blah. And for each day, it have used these tools, and it as output, it gives us the total guests, the overnight stays, the breakfast, the lunches. Always all the people used to go just for lunch and some dinner. And with this, okay, the number, very beautiful. And internally, you can see how it works. Like it uses the tool using the date, just with the date, and with this tool, it will give us a JSON in a really ugly form. So the LLM take it and put it in a table in such a way that you can see it really beautiful, not in this way that is better for us. So this is the main idea. There are a lot of functions. If you want later, you can ask. And just to conclude, then I use these Docker containers to ensure the portability. You can take your container and put it in another computer or server with the implementation of a model context protocol that enables how the LLM and the user can talk, giving these tools the subtitle for what it is used. And all of this was developed in Flowise. At the end of the day, this is a way to use and to interact with a database for someone that doesn't know anything about this. So you just talk like ChatGPT, it will give you or do some do things. Limitations. I only use one database. It was the simplest one, and I created so many functions for just a table, the database with 4 tables. It has 20 or 25. That is the normal thing. It will scale a lot. And future works. What want to do Axel? To generalize not only for the kitchen, but for as much as possible of the observatory. And thanks for your attention.
¿Me copiaste?
So half of the UPAD is, sorry, half of the DPAD is out of business after this. Questions?
Okay.
So two questions. For a regular user, what would be the interface to talk to this AI agent? It's like a ChatGPT for example, if I'm going to the observatory tomorrow and I want to do a reservation, I just open the agent and ask for the menu and ask for a reservation. Is that the way it's going to
The
work?
idea is that, yes.
Is it working?
Working already? No, because actually it's with a lot of shit, but it will be, I hope, in some point.
So what is the status of this kitchen tool? Because this is a very powerful and very interesting development. It's part of the Optimia project,
Yeah.
but you have started with probably the silliest example, which is the management of the kitchen, right?
Yes.
But I think it's a very interesting and this is going to be part. The sooner the better will be included in the Optimia. This is my understanding. So is that correct?
Yes.
And do you have an estimation on how much effort, additional effort, is required to actually integrate that within the Optimia?
This in Optimia, I think is trivial because they are containers. You just take it and put it in the server. I have already done it. So Axel can take them and put them, if he wants, in some web page and talk with it. Now the implementation to all the observatory, obviously years. I think so.
I understand this is the way that is gonna work for any subsystem at the observatory. Right?
Yes, the idea is the same.
It's the
The only
same.
thing that changed is the model context protocol, the tools that you define. So all the rest is equal.
This is going to be a significant change at the observatory management and operation.
Yes.
Okay.
As Axel said, the nitrogen liquid to put it and that you show me that the things over here, like step number 1, step number 2, do that with this would be really more easy.
Easier and safer.
Yes.
Yeah, very, very nice. And again, 3,000 lines of code looks a lot to me too. I'm not a programmer, so probably it's not, but it looks like a lot. Thank you very much. Very, very nice.
I have a question about when you say that you define all of the different tools, you write the definition and let me know if I understand. So when you ask a question to the model will process your question and try to find the closest tool that you want to use.
Nice.
Okay, but could it be the case that it doesn't, like you don't specify it enough, or you use different words and then it doesn't find the correct one?
Yes, and in that case, you should put like, ask me. I put it in the
Okay.
part, like, if you don't know something, don't assume it, ask me. Because if not, it could do like, I want to know who went to eat, when, how, what, you know?
Okay, very good.
Thank you.
Does the model understand both English and Spanish, or do you need more lines of codes to add more languages?
I think, if you want to try. I'm not sure, but it's a ChatGPT.
Okay.
If you talk with it in any language, I think it will do it too.
I see.
So in that part, if someone arrives from Italy, Spain, Nepal, whatever, you can talk in your own language. Thank you.
I'm still stuck on the 42 different programs that run that. So to implement any other access to any other subsystem, one will have to come up with n questions and write n different programs which answer those questions.
And different tools. Yes.
Different.
Yes, yes. Well, of course, you can try to generalize,
Right.
but at some point, some questions are going to be really specific. So for that reason, it's really difficult.
Awesome. The LLM you used at the end is Grok.
Yes, at the end, yes. Because Oyama, we don't have any GPU, and in a future is the idea to be all locally without any external service.
For the ones who know, Grok is Grok with Q, not Grok with K. It's the good Grok.
Did you try the open model of GPT, the new models that you can run in local? Or
The 5, what do you mean?
yes, the model, the GPT.
I have tried different GPT, but always it works almost the same because the important thing is the tool. It will use the tool, and always they give you the same structure of the JSON that I showed. But you could use whatever you want.
Do you plan to continue working, either on that project or a similar project in the future?
In a similar at the end, I think so. Maybe as an autonomous or something, but it's the idea to catch this knowledge that I have and to apply it to somewhere else, where someone wants to coach me. So.
Vega, if you're looking for someone. So if one wanted to implement this for the DPA or the UPA, because the UPA database is vast and really complicated. But it's easier to have Javi, Tamara, David.
Nowadays, yes.
Okay.
In 20 years or 10, I don't know. Because this is a scaling. Yesterday, for example, it appears a notice in LinkedIn where someone asked ChatGPT-5 to do a reasoning of a mathematical thing as abstract about complexity and that. I didn't understand anything, but it did it just by reasoning. And it can maybe even create new mathematics that is something abstract. We don't know really which one is the future.
There were two models which got the gold medal at the Mathematics Olympics. And
Crazy, yes?
and that is not something that they can have found in a database. Because I was looking at explanations. Those new problems are the people who write the problems, they make sure that the problems cannot be found elsewhere. So the problems are actually new. And there are some real mathematicians who are not able to do those. So yeah, obviously these models are getting somewhere.
Yes.
All right.
Very last
Yes.
one. Do you need the plus version of ChatGPT, or you can use the open one?
No, the other one.
The open one, okay.
Yes. I use all free. So good.
And this was the point of mentioning that it was Grok.
Okay.
Everything is running local.
Things will improve if you use the plus version.
I don't think so because of what I said before, are the same tools. So just this thing, it depends, it is bound to your tools that you define. Maybe, of course, in a future, the first week I did like a prototype with only one function that was to read, but the SQL query, it was done by another model. And this model, it can do really difficult queries just by reasoning, and later on put in another agent that took that SQL query and used this tool that is execute this. That, for example, could be a future. But you want to ponerle límites, to put limit to your model, because if not, it could screw up all your database.
Just pop to my mind. It is possible to ask the model to create the tools, or suggest tools?
To create the tools?
Yeah, based on the database that you have.
I think so, yeah.
Just to start with. No?
You can start asking and you can put it in your model context protocol. Yes.
Very helpful.
It can create itself more or less. You must be cautious with it.
Of course. Getting ideas, it's
Do not create new tables. Do not delete entries.
Do not delete anyone that wants to eat today. Yeah. Coffee?
So if there's no more questions, if there's no more questions or comments, let's thank and congratulate the 3 students.
the advisors of the users.
And no coffee.
Solo lo enchufo.
No, yo tampoco porque